Hello students, now let us understand a force versus displacement curve. So let us analyze the equilibrium state and stable equilibrium and unstable position of a oscillating body. So in this curve, force and displacements are plotted. Force becomes 0 at two positions, that is at point A and at point B. Point A force is 0 and also at point B force is 0. Let us displace the body from this point A slightly to the right. A force is developed which is negative in direction. If I displace the body towards the positive x-axis, force will be generated in the oscillator which is negative. So it is obvious from the definition of simple harmonic that force is proportional to minus displacement. So it is true in this case. If I displace the body towards left, that is negative x-axis, then force will become positive. Body is displaced to the left hand side, that is negative. Then force developed is in the first quadrant, that is positive force. That means again this follows the definition of simple harmonic motion. So at this point A, total force is 0. Therefore we call this position as stable equilibrium point. The condition for equilibrium is force must be 0. At both these points A and B, force is 0. But how B is different from A? Let us analyze. At point A, total force is 0 and force acting is a restoring force that tries to bring it back to the position A. Therefore, this point A is called as stable equilibrium and force is 0. Now, at this point B, if I displace the body towards positive x-axis, force developed is positive, and if I displace it towards the left negative side, force is again in the negative direction. Therefore, even though at this point B force is 0, the body is not stable. So we call this point as unstable equilibrium point. At both these points A and B, force is 0, but at point A the body comes back to the same point even if I apply force, but at this point B it doesn't return back to the point. So now let us understand how does a potential energy versus position curve look like. So here is that graph. At point A, energy is minimum. For any system to be stable, what is the condition? Its energy must be either 0 or minimum. If I take slope of this curve, position versus potential energy curve, slope is 0 at this point. So we'll get 0 slope at point A and again 0 slope at point B. The slope of the valley will be stable point and slope of the peak is unstable point. Therefore, for stability, the condition is that du by dx is equal to 0, and that is what force is equal to 0. The force acting at point A at stable equilibrium is 0. This must be negative of du by dx, as this is decreasing curve and becomes 0 at this point, whereas this will be positive du by dx, but that is unstable point. Now I have to find out the force constant for any oscillator. Now let me consider potential energy as a function of position. So u is equal to some function of position r, and this is minimum. This potential energy is minimum at position r is equal to r0. That means about this point r0, the particle is performing simple harmonic motion. So if I displace this system by a small displacement dr, then a restoring force df is developed which is proportional to the negative of displacement produced, or I can write this as df is equal to minus force constant into dr. Now I have to find out what is value of this force constant k. So k is equal to minus df by dr. Now we know that at equilibrium position the potential energy is minimum. Therefore we know that For any conservative force F, it can be derived from its potential. So du by dr is equal to F. Let me substitute this value in the previous equation. Therefore, I get force constant K equals minus d by dr of what is F? F is minus du by dr. Therefore, we get second derivative of potential energy with position. So it is d squared u by dr squared is equal to force constant K. And this force constant is related to angular velocity omega, as omega is equal to root of K by m. So using this value we can find out omega and hence time period of the oscillator.